Right, so the first question is looking at the way the units can be written in different ways. It says the power of 1 watt is the same as, well, we hopefully know the equation for power, which is power is energy over time. Now if we look at what the units of these are, well, energy is in joules, time is in seconds, so therefore 1 watt, which is the unit of power, is equal to 1 joule per second. So we would go with B. Number 2, pressure of pascals is the same as, well, pressure is equal to force over area. Okay, and what are the units of force and area? Well, force is in newtons, area is in square meters. Okay, so 1 pascal, which is a unit of pressure, is the same as 1 newton per square meter. Magnetic fields can be indicated using lines. The arrow on the magnetic field line shows the direction of the magnetic field. It always goes from north to south. Equal spaces between magnetic field lines show that the magnetic field has uniform strength. Okay, hopefully we can remember that wherever the lines are closest, the field is strongest. Question 2 is about electromagnetic waves, and we're looking at infrared, UV and visible, and they want you to arrange them from longest to shortest wavelength. And it's just something you have to remember, really, that infrared has got the longest wavelength of these, visible in the middle, and UV has got the shortest. UV has got the shortest wavelength. Name 2 other types of electromagnetic waves. Well, you've got X-rays, you've got radio, you've got microwaves, and you've got gamma rays. Any of those 2 of those are acceptable. Now we're looking at ultraviolet waves in particular. It says they can be dangerous, but what are 2 uses of them? Well, one use is that they can be used for detecting forged banknotes. If you put a UV light on certain banknotes, then you will see a watermark that's only visible in ultraviolet light. Another use is that UV waves can be used to treat water, to kill bacteria, and to make it safer for drinking. But obviously, as well as being useful, UV waves are dangerous. How are they dangerous? Well, they can cause cell damage, and this cell damage then can have a number of effects. One of them is that it can cause an increased risk of skin cancer. Another one is that it can cause damage to the eye, and it can reduce the quality of your sight. Question 3. So the diagram shows a piece of card and 2 wide bar magnets. Add to the diagram to show the shape of the field and the direction. Now when it comes to the shape of the field, okay, within the kind of bar magnet side, and it'd be nice if you do this with a ruler. Unfortunately I can't, as I draw on this computer. The field is going to be uniform, and that means that all of these lines should be parallel and roughly equal distance apart. Oh, just realised I've made a mistake, wasn't looking what I was doing. Field lines always go from north to south. So I need to make sure that my arrows are going the opposite way to the way that I originally drew them. Okay. Outside of the bar magnets, the field won't be uniform. Okay, it will still go from north to south. We'll get something more like this. Okay, but for this question, I don't think you really need to include those bits because it says between the magnets. Okay, and what they want to see is that between the magnets the field is uniform, so parallel lines equal distance apart, with the arrows going from north to south. You're then asked to describe how to investigate the shape and direction of the magnetic field between the magnets. Well, the best way to investigate the shape and direction of the field is to use plotting compasses. I think you'll get a mark just for mentioning that. Okay, and that the needle will show the direction, again, as we said, goes from north to south. So what you'll then do with these compasses, now each time you put a compass down, you're going to put an arrow in the direction of the needle, and then you're going to move the compass to the end of the previous arrow. So for example, if the first arrow is pointing in this direction, you're going to put the next compass here, and you're going to put the next arrow in. You're then going to look for where this compass points, and you're going to keep moving the compass around. Now we then place a rod, metal rod, in the magnetic field. Now this magnetic field is at 90 degrees to the rod, okay, and therefore it's at 90 degrees the direction which the current is flowing. So the current is flowing from positive to negative, so it's coming through here and it's going at 90 degrees to the magnetic field. Now it says describe the effect on the rod. Well, hopefully you're thinking of Fleming's left-hand rule, okay, where we want to know the direction of motion. So that's being given by your thumb. So if you line up your first finger with the magnetic field, your second finger with the current, make sure you're using the left hand, and what you should find is that your thumb is pointing upwards, okay? So we're going to say then that the rod experiences a force, but we also want to say about the direction, and that direction is going to be out of the page. So coming straight out towards us. So question 4, we're looking at a photograph of an old brass mass. It says it's 500 grams. Student puts it on electronic balance, and it's not exactly 500 grams, it's 498.2. And the student concludes, I think the electronic balance is not working properly. Now you've got to evaluate that. Now you're evaluating the conclusion, so there's no mark for saying that the student's statement is correct or incorrect. We're looking for points that basically might give reasons for why they wouldn't be the same. So the kind of things I'm looking for, well, the balance may not have been set to 0, okay, so if it wasn't already 0 before the mass was put on top, then it's never going to give a particularly accurate result. It also mentions the mass is old. Well, it may have been that the mass was once 500 grams and that over time its use has meant that it's been worn down by a small amount. Probably the most likely thing though is that the two values are close, and the 498.2 grams is within about, well, less than 0.5% of the value it states, 500 grams, and that to me seems to be a pretty acceptable limit for a manufacturer to quote. You know, whenever you see measurements quoted, they're never going to be exact. There's always going to be some kind of uncertainty in it, and that seems a reasonable uncertainty. And the student then wants to find the density of the mass. He firstly obtains the correct value for mass, and now what else must he do to find the density? 3 marks. We need to write down 3. Well, the first thing is that he needs to find the volume. Well, how's he going to find the volume? Well, the most likely thing to do is to use a displacement method. So he's going to put the mass in the water. If he knows the initial volume of water in something like a measuring cylinder, and then looks at the final, then the difference in volume is going to be the volume of the mass. And then he has to do a calculation, because to work out density he needs to divide mass by volume. Number 5, a racing cyclist practices by riding around a track. The student wants to find the average speed. Describe a method that she could use. Well, first thing is to realise then that speed is equal to distance over time. Okay, so what we're looking for then is that we need to know distance, we need to make a measure of distance, and we need to make a measurement of time. Now what are we going to use to make those measurements? Well, the distance, it could be that we use something like a trundle wheel, or it could be that we have a known track length if we're in a velodrome. Now for time, what are we going to use there? Well, it's going to use a stop clock, okay, or some kind of electronic timing. And in order to increase reliability, we will probably choose not just to do one lap of a known track. We'd either do a number of laps if that was the case, or we take repeat readings. Okay, so one of those two to make sure that we get a more reliable value. Number of laps or repeats. Right, question 6. It's about the solar system. Hopefully part A is easy. The object at the centre of the solar system is the Sun. And Earth and Mars are planets in our solar system. The table below shows some data. Now you've got to calculate the orbital speed of Mars in kilometres per day. You know, speed is equal to distance over time. Okay, so we need to know the distance that it travels in one orbit in kilometres and the time it takes to orbit in days. Now the distance then is going to be the circumference of the orbit, which is going to be 2 pi times the radius, and capital T is for the period. So if we put our numbers in here, 2 times pi times Mars, we're looking at 250 million kilometres, and we're going to divide that by 690 days, and the answer we get then is 2,300,000 kilometres per day, so pretty quick. Now it says the distance between Mars and Earth, so Earth and Mars, varies between 100 million kilometres and 400 million kilometres. Explain why this distance is not constant and use a diagram to help. So we've got the Sun at the centre of our solar system. We've got Earth in its orbit here. I've drawn it circular. It's not quite circular, it's elliptical. And then we've got Mars in its orbit a little bit further out. Now, as the two planets orbit the Sun, then they're not going to be having exactly the same period to get round. So when the Earth has done one cycle, Mars won't have done a cycle. And what that means is at another point in the orbit, a later stage, when the Earth has got back to the same point, so it's gone all the way around, okay, Mars won't have. So Mars will only have gone part of the way round, and therefore the distance is now going to be much further than it originally was. So if this is the original distance between them, now this distance is going to be much greater. So because they are both orbiting the Sun, but they are orbiting it with different periods, the distance is going to change. A visible light from Mars reaches the Earth, and it travels at the speed of light, 300 million meters per second, or 300,000 kilometers per second. Show that when the planets are 170 million kilometers apart, it takes 600 seconds for light to travel. And we know that speed is equal to distance over time, so that means time is equal to distance over speed. Now, if the planets are 170 million kilometers apart, okay, but the speed at which light travels is 300 million kilometers per second. Well, because they're both in kilometers, or they have kilometers within the unit, we don't have to worry about converting them into anything else. So if I do that sum there, and if I cross off 5 zeros off each side, I've got this sum, and the answer that we get, if I round it to two significant figures, is 570 seconds, which is approximately 600 seconds. Now, scientists land a remote-controlled vehicle on Mars, and it sends back images, and sometimes these images shows rocks that could damage the vehicle. A scientist on Earth sends radio signals that control the vehicle. The vehicle's kept at a low speed of 0.04 meters per second. Why is the speed? Well, one reason is if it does collide with a rock, there's going to be less damage. It's also going to be less likely that there's going to be a collision, because the low speed is going to reduce the stopping distance, makes it easy to stop and it's going to require a smaller stopping distance, because the time delay between sending signals from the Earth to Mars is going to add an extra reaction time. So rather than just a normal reaction time you'd have here on Earth, you've got to add on that extra fraction of a second in which the vehicle is going to keep moving, even though we're trying to stop it.